Hello everyone, my name is Dervla O'Reilly, Senior Event Manager with MIPI Alliance, and I'm going to be your moderator today, so welcome. Today we're presenting the second webinar in a series of 3 audio webinars taking place, and the final one will be tomorrow. In this series, the leaders of MIPI's audio and software working groups will dive into the full portfolio of MIPI audio specifications and provide explanations of each specification and share their insights into future developments. Yesterday's session provided a primer on MIPI audio specification and giving a system-level overview and high-level introduction to all of MIPI audio interfaces and the supporting software specifications. So building on yesterday's session, today's presentation will take a more in-depth look at MIPI's latest audio advancement, the new MIPI SWI3S audio specification. Tomorrow in the final webinar, we'll examine the growing suite of MIPI audio software specifications and tools. Let me tell you a little bit about our speakers today. We have 3 experts in the house. Aruni Nelson, who is the Principal Engineer at Intel Corporation and also the Chair of the MIPI Audio Working Group. We've also got Neil Warren, Technical Consultant with MIPI Alliance and former Chair of the Audio Working Group. And we have Christian Jankner. He's the Co-Vice Chair of the MIPI Audio Working Group and also Director at Infineon Technologies.
Today, we will be talking about SoundWire I3S, or SWI3S, the newest audio interconnect developed by MIPI's Audio Working Group. And in this session, we'll walk through 4 key areas. What is SWI3S? We will start with an overview of the interconnect, how we got here. We will take a look back at the evolution of audio buses leading up to SWI3S. And inside SWI3S, we will talk about the physical and the protocol layers of SWI3S. And then we'll see where SWI3S fits in, and then we'll wrap up with Q&A session. So let me jump ahead here. So let's start with what is SWI3S. Now, if you attended yesterday's sessions, some of the content will seem familiar, and it is intentional. So SWI3S, or SoundWire I3S, is the newest member of the MIPI audio family, the less talkative cousin of SoundWire. It is a 2-pin, multi-drop, half-duplex interconnect, which is designed to deliver both the audio data and control with exceptional efficiency and scalability. It builds upon the existing MIPI technologies, such as SoundWire and SlimBus, and it takes a major step forward to meet the needs of today's and tomorrow's embedded audio systems. SWI3S is capable of delivering bandwidths up to 76 megabits per second, which is more than 3 times that of SoundWire's 24 megabits per second over 2 pins. But beyond the increased bandwidth, SWI3S has been designed for robustness, for flexibility and power efficiency across a wide range of form factors, from compact earbuds to large audio systems. It supports 2 physical layer options, forwarded bit clock single-ended, which is ideal for short, low-power PCB traces, and differential low voltage, which offers operating voltages as low as 50 millivolts, and link lengths reaching up to 2 meters, giving you EMI resilience, both susceptibility and emission. So this makes SWI3S both low power and long reach. To further enhance the signal integrity, SWI3S also includes standardized data scrambling techniques, and the results are cleaner signals, lower emissions, and more stable audio transport in electrically noisy environments. The diagram here shows a typical SWI3S link, which consists of 1 manager and up to 12 peripheral devices. And each peripheral can contain multiple data ports and handle multi-channel audio without increasing pin count or bus complexity. Now, SWI3S is built around a row-based structure of bits and symbols, which offers flexible bandwidth allocation between different functions like audio streaming or control commands. SWI3S also features a robust command channel between the manager and the peripherals, And with respect to synchronization, SWIS has the most advanced and flexible synchronization mechanism with greater control and the scope of synchronization. Synchronization points can be applied at the row boundaries and across multiple devices or across data ports within a device. SWIS also provides comprehensive link management, including control for power states, link configuration, and synchronization recovery. And in addition to link power states, SWIS supports peripheral low power states, where a peripheral can dynamically enter low power or dormant states and then resume operation in sync with rest of the system, which makes it ideal for always on and battery sensitive designs. So in summary, SWIS represents the next evolutionary step in embedded audio connectivity, which is required by the next generation of intelligent connected audio systems, whether you're designing for wearables, mobile, PC, or automotive. SWIS gives you an elegant, future-proof interconnect, one that simplifies integration while delivering the exceptional audio performance. So just to get a level deeper and see how SWIS architecture is structured. So like many communication protocols, SWIS follows a layered architecture where each layer has specific functionality. We will start from the bottom, the physical layer, and work our way up to the command and payload stacks, which handle control and data operations. So at the bottom, we have the physical layer, or the PHY, which is basically the analog portion. This is where the electrical signaling happens, the actual voltages, the timings, the line characteristics that carry any data between the manager and the peripherals. And as mentioned earlier, SWIS supports both single-ended and differential PHY, but the PHY interface layer is PHY independent, meaning the upper layers don't need to know the electrical details. They just exchange the bits through a common PHY interface abstraction. Moving up, now let's look at the command stack. This is where the system intelligence resides. The command stack handles control, configuration, status, and interrupts, the things that make the hardware respond to hosts, commands, or instructions. And here is how the command stack is structured. So we have the peripheral command model for registers on top, and this defines how the manager or the host accesses registers, whether they are SWIS native or non-SWIS registers. And we also allow both local and remote register models. Then we have the commands layer, which defines the set of operations or commands that can be sent over the link. For example, we have commands like ping and unblock to check the peripheral status and restore communication. We also have commands that announce the stream sync points like the SSPAs, and commands to handle low power transitions. We have read and write commands for register access. We have commit request commands for synchronized updates to register sets in one device or across several devices. We also have additional commands for PHY level calibration. And then we have the command transport protocol, which defines the framing for command transactions, how transfers, phases, and bytes are grouped, how timing is aligned, and how acknowledgements are handled. And then we have the control data stream bits and symbols. These are the actual on-wire representation of command traffic. They use standardized encoding schemes such as 8B, 10B encoding. We have idle bits and calibration patterns, etc. Now let's look at the payload stack, which is used mainly by audio streaming components such as, say, analog to digital, digital to analog converters and amplifiers. And this stack defines how payload data, the actual audio samples, are represented, formatted, and synchronized. And the payload stack also includes several sublayers, and SWIS supports multiple data formats like PCM, PDM, 2's complement, 1's complement, etc., giving flexibility across a wide range of audio converters and DSPs. And then we have the payload model, which represents the sample streams, the channels, and stream synchronization points basically all the constructs that enable precise alignment between devices during streaming. And then we have the data port layer, which maps directly to the data port registers in each peripheral. And these registers define how each stream or channel group connects to a logical audio path in the system. And then at the bottom, we have the payload transport protocol, which defines how samples are carried across the bus, including sample intervals, grouping, horizontal start and count, offsets, and optional scrambling. So in summary, you can see how each layer is abstracted and modular, and both the control command and the payload stack, they use the same physical layer and the same 2 pins of the interconnect. Now let's quickly look at what SWIS was built upon. And this slide here captures how the MIPI Audio Working Group continues to drive the evolution of audio connectivity, advancing the technology through a suite of standardized MIPI audio buses. The Venn diagram you see here highlights that journey, how SWIS builds upon SlimBus and SoundWire, extending their strengths and adding brand new capabilities, some of which are planned for SWIS version 1.1. So it all started with SlimBus, which is short for Serial Low Power Interchip Media Bus, which was introduced by MIPI back in 2008. And the goal was simple. It was to replace older fragmented interfaces or interconnects like I2S, TDM with I2C, etc., which were great for their time, but limited in scale. These older buses are point-to-point. If you need more channels, you have to add more buses, and each adding more complexity, more pins, more cost. And SlimBus solved all that. It gave us a 2-wire message-based multi-drop bus that could carry both audio and control over the same connection. It supported multi-channel audios, different sample rates. In short, SlimBus unified the audio and control. It reduced pin count, and it set the foundation for modern, low-power, intelligent audio systems. Now, fast forward to 2015, when MIPI introduced SoundWire. SoundWire kept the simplicity of SlimBus, but it added a stronger focus on efficiency, on latency, and control. And some of the key enhancements were dual data rate operations for higher throughput, direct register accesses for finer software control, features like clock pause and peripheral initiated wake for low power operation, and bulk transfers for use cases requiring large data transfers such as firmware download. But as the system complexity grew, the team saw another opportunity to take audio interconnect even further. And that's where SWIS enters the picture. SWIS is also a 2-pin multi-drop bus, but it pushes the bandwidth up to 76 megabits per second, supports both single-ended and differential PHY for long reach. That means SWIS is equally at home inside tiny earbuds as it is in large audio systems. And the differential low voltage PHY brings exceptional noise immunity and low EMI, which is perfect for cases like microphones near RF antennas or dense mixed signal environments. And to go further and further improve the signal integrity, SWIS adds standardized data scrambling, which minimizes EMI peaks and improves link robustness. But beyond these physical improvements, SWIS redefines what's possible at the protocol level. It supports fine-grained synchronization. That means more precise timing for multi-device use cases. It enhances reliability with CRC-protected control channels, adds error counters, robust token handling. Encoding has also evolved. We have 8B, 10B encoding, which is applied to the SWIS control data stream bytes. And the setup time, it's fast. Link bring-up now takes approximately about 6 milliseconds, which is down from roughly 33 milliseconds in SoundWire. And other than that, SWIS expands the control bandwidth. It allows block reads and writes, gives you more data ports, more channels per data port. So in summary, SWIS is not just a next version. It is a major leap. and I'm repeating myself here, but Swiss is faster, it is quieter and smarter, and it scales across device classes with improved timing, power efficiency, and signal integrity. So from the smallest wearable to the largest audio systems, Swiss provides the foundation for the next generation of unified, high-performance, low-power audio. With that, I will hand over to Neil to take us through the journey that has brought us to Swiss.
So over the next several slides, I compare a few elements of various audio interfaces, but first, a little bit of history. In the beginning of this century, some engineers like Gerald Jones at Apple and Jens Christian Poulsen at BlackBerry were thinking about synchronization patterns as a way to save pins in an audio interface by having synchronization embedded in the bit stream. And SoundWire Classic wound up using both a static and dynamic sync pattern, static one to simplify looking for it, and dynamic to increase the probability that you actually found the correct alignment and synchronization as opposed to finding the pattern in noise or random data. During Swiss development, we realized that a robust command protocol can be used instead of the sync pattern. So in Swiss, taking advantage of a comma character in the 8B, 10B, we essentially reuse the control stream parser as the synchronization source. That saves bandwidth used on the link for synchronization and also increased the robustness and the flexibility of synchronization. Another influence is Sonnet had used a 2D or matrix-based bandwidth allocation scheme. Slimbus used a nibble-based one from a linear list. Last decade, Wolfgang Furtner and Andrew Fitting were looking at multi-drop differential with the little wrinkle of not using the traditional high-power current mirror driver, but dual single-ended transmitter, or dual single-ended differential transmitter, we call it, which can be much lower power for driving the line, and then traditional modest gain, low power differential receiver, and a PLL to find timing. Note that Classic and Swiss borrow the matrix approach, the 2D-dimensional array bandwidth description to form circuits as opposed to datagrams. They borrow that from Sonnet. SoundWire Classic carried forward the optional slew rate control that was first shown in Slimbus, and the synchronous change in transport bandwidth, also from Slimbus. Slimbus only supported power of 2 steps in bandwidth, allowing some crude trades between available bandwidth and power consumed. Classic and Swiss, using the 2-dimensional approach, allow finer gradations in power bandwidth trades. The Swiss synchronization approach is a little bit more similar to USB and SPDIF, and SoundWire and Classic and Swiss both convey PDM format data, that is sigma delta modulator or delta sigma modulator, depending on which paper you read first, as well as I2S and PCM as efficiently or more efficiently than the older interfaces with the same interface as those interfaces is displacing. Here I have a slide kind of showing two categories: transports that were designed to interface between boxes, like USB, and transports that interface within a single box. And then I try to grade the synchronization cost. The vertical axis is a weighted sum of the bandwidth consumed on the link and the complexity of the circuit used behind the scenes. Sonnet is way up at the top because some implementations used atomic clocks. USB high speed uses a violation of the bit stuffing, I think like something like 47 bit times. So it's using quite a bit of the bandwidth for its start of frame markers. SPDIF uses a biphase mark coding violation, which complicates the clock recovery efforts. I2S and PCM are near the top because they actually have a whole separate wire for frame sync. As I mentioned a minute ago, Classic uses static and dynamic synchronization pattern in the bit stream, but that uses a significant fraction of the control bandwidth. Swiss uses the command protocol itself, and there's essentially almost no circuitry needed to synchronize once you've established synchronization. It's very small, so it's the cheapest in terms of bandwidth and circuit complexity. This is a bit of an eye chart, and not shown on here is PDM, which is the most common digital microphone interconnect, as well as data format. In this presentation, we mostly use it to describe it, a data format, that is the delta sigma modulator format. But on this slide, I think about it as a transport. Mini microphones today support multiple modes, like a low power mode, high performance mode, but the de facto PDM transport lacks a control channel, and the clock is currently used for control. Unfortunately, the so-called low power mode both raises the noise floor and lowers the so-called acoustic overload point. It's actually a clipping point in analog, I believe, when you're in low power mode. A low power mode where you could move those independently when you wanted to save power would be much more useful. It's also handy to have a control channel for debug and failure analysis. SoundWire Classic and Swift both provide this control channel for microphones. As I mentioned, 8B, 10B combined with robust tokens. Those are tokens where the Hamming distance between valid codes is quite high. And checksummed messages are like a belt and suspenders approach to robustness. So Swiss has a very robust protocol, error counters for detecting bad tokens, detectors of synchronization to give when you're starting up an audio stream, you know everything's in place as it starts. Of a rich set of commands and error counters to help with the robustness. SoundWire Classic only provided synchronization at the frame rate. And if you were going to transport multiple sample rates at the same time on a bus, like 44.1 kHz and 48 kHz, which are possible in Classic, you can only synchronize at the least common multiple, which is 100 Hz. Swiss has independent delivery of synchronization to various groups, allowing the system integrator to choose a synchronization rate independently for each flow rather than have it be dictated by the math. Okay, just explain what this slide is. Going across from left to right are various models of traffic, and this is showing measurement from these models. Column 1 shows a single microphone in low power mode, probably running at 768K bits per second or something. And then the control channel has a similar bandwidth. That's how we get to about 2 megabits, rounding up. Column 2 shows 2 microphones in low power mode. Column 3 shows 1 microphone in high performance mode, etc. So the traffic goes up as we go across. Comparing the red versus blue is contrasting the difference in emissions. Here we're saying emissions is the toggle rate times the voltage squared. Over time, rise in voltage, which is, you can talk to Maxwell about that. SoundWire Classic has a forwarded bit clock, and Swiss has 1 clock per row because it's counting on the PLL to determine where the bits are within the row. So the biggest difference between red and blue is actually due to the lower voltage made possible by differential signaling. And note as you go across that the red rises more steeply than the blue. And the reason for that is that Swiss only has 1 clock per row, whereas Classic has to have an edge per bit. So between being low voltage differential and actually having fewer edges per bit than Classic, Swiss saves both power and emissions. Actually, yes, and here's the slide talking about power. So in the previous slide, I showed the reduced emissions. And here we're showing the link power, and you might say, why is the story not as rosy as it was for emissions? And that's because we've included 80 microwatts for a PLL of sufficient quality to place and sample the bits at the right place in the row. On the left, you can see that SoundWire Classic achieves quite low power. When Swiss is used in the single-ended mode, it achieves similar power. As you move to, but here we're showing DLV, which required the PLL. As you move to the right and higher bandwidth, and especially larger distances and larger capacitances, Swiss starts to win on power. So as we mentioned before, we have reduced pin count compared to a typical TDM/I2S plus either I2C or SPI plus a GPIO that you might need to use to connect an amplifier. And we have power and efficiency that goes hand in hand with reduced link power. We accommodate larger form factors like a television, a car door, larger all-in-one computers, which all sometimes have a large ground shift, and that's where the differential is quite helpful. Here we're using PDM as a data format as opposed to a de facto interconnect standard in bullet 11 there, where we show that we can concurrently transport those with similar latencies to existing interfaces. In addition to the listed benefits, we've standardized the register set, and that allows operating systems to support devices without requiring a custom driver. And we think going forward, that's going to be a really appreciated economy. The other differences, here we go. And also comparing to SoundWire, the big difference between Swiss and SoundWire is that in SoundWire, within 1 bit, a device had to finish driving to satisfy the hold time for all of the devices on the bus, stop, let the bus go to high Z, allow another device to take over driving, and it had to drive and settle the bus in time for the setup time of the next clock edge. So all of that has to happen every bit, and every node on the network has to reliably see every bit because every node is checking parity. So this gave some robustness in SoundWire Classic, but it limited the length. And it also meant that sometimes we were allocating more time for one thing or another than was really needed in the system, especially if a single device owned multiple bits in a row. So Swiss uses a parameter-based time allocation scheme where you explicitly schedule the handovers if you need them. And if you needed a longer bit time for a particular pair of nodes to communicate, it's only when that communication is occurring that you need to use that wider bit time. So this is one of the reasons that Swiss can support longer trace lengths and higher bandwidths. And then the differential signaling also allowing a greater ground shift helped increase the lengths. And the lower voltage gave us greater power efficiency and the lower EMC. Another difference is the protocol layer in Classic only supports 16-bit addresses, so we did need to add a segment type register to allow up to 2 gigabytes of addressing. And Classic, if you don't support the optional bulk protocol, which is really essentially yet another protocol making use of other data bits, Classic messages all contain an address and a byte, so firmware download takes quite some time, whereas Swiss supports a single 256 byte write, allowing much better bandwidth efficiency, which I think Christian will talk about a little bit as he gets into it.
Okay, thanks, Neil. I take over here. Some words about the physical layer interface. On this slide, you see on the left side, you see a graph that shows the bus from the perspective of the peripheral and the perspective of the manager. And in both cases, you see 2 blocks. So one rectangle that shows the link is inactive, and down you see a rectangle that shows link is active. And now we have defined a special link control phi that moves the bus from inactive to active. This is a simple CMOS, uses a simple CMOS signaling and has a relaxed timing so that it can operate with very low power. And it is used to do a bus reset, to do the so-called cold start, so when the bus initially starts. And during this cold start, the bus members, the peripherals, get a phi number. And this phi number defines then which phi should be active during the link active state. This is called then the audio mode phi. Also, the peripherals can use the link control. So, of course, they have to monitor the bus whenever the manager starts the bus. But they can also send link start requests for wake up or for cold boot if they support this. Going now to the link active, here the audio mode PHY take over. So currently we have defined 3 PHYs, but basically there are 2 groups. So one is a single-ended PHYs, and one group is a differential PHY. So the single-ended PHY, it's a forward bit clock single-ended PHY cord. It has one clock line, audio clock line going from the manager to the peripherals. And a bidirectional data line. So it says CMOS-like levels, 0.9 to 1.8 volt. Maximum data rate is 50 megabit. However, we have defined here 2 single-ended PHYs. One that uses no handover UI if the bus owner changes. This goes then up to 12 megabit. And the so-called PHY 2 goes up to 50 megabit. But when the bus owner changes, there's a handover UI or handover bit that is not used by any transport to mitigate the timing. Typical applications are small and power-sensitive systems. So all in all, also the area on the chip real estate is comparable to SoundWire. However, it has still improved emissions. It has a controlled rise fall times. It has 2 types of rise and fall time slopes. We call it voltage ramp. This is with a constant impedance, or a conductance ramp. This is when the output impedance is controlled and has finally then a defined value. You can also select which output impedance you use during operation. And the other type of PHY is a differential PHY. A differential low voltage PHY goes up only to 400 millivolt, which saves a lot of power on the bus. Its speed is 76 megabit. It's typically used for larger systems, higher bandwidth needs, and if there is EMI sensitivity. There is still a clock transferred over this differential signal. So as Neil mentioned, we have a kind of a matrix organization for the data pattern, and in every, so it consists of rows and columns, and in every row there's an audio grade clock embedded in the data stream. However, it needs a clock recovery, and this of course consumes some static power, as said before, and some area, but is highly beneficial when we go to high bandwidth. So then the next topic would be some words about the protocol. So as just said before, the bits that flow over these PHYs can be seen as a sequence of rows. In this figure, you see maybe a quite busy figure, but you see one row starting with column 0, S1 is the bit, to column 15. So you see a row with 16 columns. And there are different types of bits transferred in a row. By the way, the row can be 4 columns, it can be 32 columns. So this gives then always a trade between bandwidth, control bandwidth and data bandwidth, because in every row there is this light blue C transferred. This light blue C is a control data stream bit. Other bits, data bits like D1, D2, these data bits can be grouped, like you see here, and this is D1 stream, or they can also consume 2 of these columns if the bus structure is more tricky and the bit has then longer time to settle. You see these double arrows, these are handover bits. Whenever the bus owner changes, you need to spare a bit. And you see also the S0, S1, and this is the audio grade rising edge clock that is also embedded in the data stream. So you need clock recovery, yes, for clocking in the bits, but not this needs not be a audio plate PLL. Going one step further to the command protocol, this was mentioned anyway already by Aruni quite in detail. It is PHY independent. And if you remember this light blue control data stream bit, which is sent every row, so 8 of these bits is 1 byte. This byte is then coded into with a 8B, 10B encoding for more robustness to 10 bits. And so in 10 rows, one symbol is transferred. And larger sequences of these symbols are called phases. And these phases have then a defined ownership for each byte. So in these phases, you can also embed, or you would typically also embed a command. And also Aruni mentioned the commands, so typical commands are ping commands to collect data, peripheral status, so is a peripheral still attached or not? Does it has an interrupt or not? Read and write commands, commit commands for synchronization. SSPA, synchronization point announcement commands to ensure that data ports stay in sync, and calibration commands. If we look now at a phase, how does a phase look? So you see on the right-hand side the figure. A phase starts, so every block is one symbol, also this 10 rows. The start of the phase marker is the first symbol. So this is a unique 8B, 10B comma code that never ever should appear in the data stream. So it's a unique code that marks the start of a phase. This is then followed by a phase header. The phase header is also compiled by robust tokens. Robust tokens are tokens selected, 16 selected tokens with a large Hamming distance into them, and they don't change their running disparity. This is then the phase header is then followed by the packet. In this example, it's a write phase. The manager packet includes opcode write, address, and write data. This manager packet is then protected by a CRC. And then the bus ownership changes because the manager writes to the peripheral, and the peripheral needs to answer if the command was executed in the right way. So this is write OK answer, and in between you see a protocol spacer that gives the peripheral time to decode the command and to execute the command, as well as in later versions we plan to have segments. And if the command crosses these segments, there's always a row lost when you change from segment to segment. So this is also a precaution or a future-proof feature already. Going to the audio payload protocol, on the left you see the same similar picture out of the standard that Aruni already described. I would like to show that the payload can go not only from manager to peripheral and peripheral to manager, but also from peripheral to peripheral. It can also go from one source to multiple destinations. It supports exotic timings, like a lower sampling rate or a higher sample rate interval or based link. Or it supports also flow control. So when a source can signal when data is available, or a sink can signal when it's ready to receive data. Streams can contain more than one channel, and this channel can also go, for example, one N channel stream can go to N one channel sinks, this case amplifiers, for example. Then the scrambling was already mentioned, which removes signal-dependent crosstalk and DC content. This is by default on, can be switched off, but it's a very useful feature. Can also be used for testing to define, it defines a well-defined pseudo-random bit sequence. And the data board provides prepare and ready mechanisms. So this is used for the audio function outside the Swiss interconnect. So for example, if you start a microphone, you need to start the analog part of the microphone, which probably needs some time to settle. And so the manager typically would send a prepare command, then the analog part starts. Then the microphone can signal a ready. This is read by the manager, and then the manager enables the data board, and then valid data is transferred. How does now this matrix-like row column structure look like? So this is maybe a little more complicated example, but you will later say we have tools to support you for this design. So here you see in this graph, you see again a row out of 16 columns. And this row, this pattern is repeated every 64 rows. If you have now a row rate of 3 megahertz, 3 megahertz divided by 64, you get a sample rate of 48 kilo samples. So if you look, for example, in column 4, 5, and 6, so you see D1, you see 24 bits, D1, these are repeated every 64 rows. This means you have a sample, 24 bits with 48 kilohertz sample rate. But you can also combine this with different sample rates, like in column 8, you see a D7. D7 bit is sent in every row. If the row rate is 3 megabit, and imagine D7 is then a BDM stream of 3 megabit, for example. If you want, maybe if you want to have a more close, a better description of this, I would recommend to read chapter 4. The technical overview in the SoundWire specification. It's just 40 plus pages and gives really a very good and detailed overview. And I think also this figure is from this section. So this is then explained in detail. What also will help is the Swiss visualizer tool. This is public available on GitHub. This was the intention was to help the system designer to find a correct configuration. And this tool, in this tool, you can select or change starter board parameters, like when the bit starts in a row, how the bits are grouped, if this is a source or a sink, and so on. And it will tell you if the configuration is correct. For example, if you have a bus clash or other problems. So I think Neil talked yesterday about this tool in more detail. Now let me continue with just 2 slides about the operational model. So like a day in the life of a manager. So what the manager needs to do in context of Swiss. On the right side, you see again a figure. This is in this case the manager link control state machine. On the upper side, you see the inactive link behavior, and on the downside, not so detailed, you see the active link behavior. In the inactive link behavior, the manager needs to start the bus, and this is done then with this manager link state machine. In the active link, so after the bus is started, the audio files are selected. Then it is in the active link state. Here the manager needs to provide so-called command confidence, because each peripheral needs to track the CDS bit stream and needs to answer commands given to them. And the typical command is then a ping command that is addressed to multiple peripherals and gives the manager the knowledge, is this peripheral attached or not, or is there any other problem? And yes, it has, of course, also to manage and needs to configure then the peripherals, establish data port traffic, audio traffic, and also he needs to react on events. What a peripheral needs to do, on the right side, you see the same, let's say, state machine. It's the peripheral perspective, inactive link and active link. In inactive link, it needs to monitor the bus with this link control file and sees if, needs to check if the manager starts the bus or there is a bus reset, or it needs to go into a low power mode like sleeping. In active link behavior, it needs to maintain its command confidence. So it always needs to track the CDS bit stream, check for the start of phase marker, this unique K code, and then also check if this address is, if this command is then addressed to this specific peripheral, needs to execute a command, report interrupt, and so on, and of course establish audio traffic. Okay, with this, I give back to Aruni to continue.
Thank you, Christian. So now that we have talked about what Swiss is, how it's structured, how we got to Swiss and how it works, let's take a look at where it actually fits in the real world, the kinds of products and systems that can benefit from it. And one of the biggest strengths of Swiss is its scalability. It is not tied to a specific form factor, power level, or application type. Instead, it is designed to meet the needs of all computing segments, from the smallest earbuds to the largest audio systems. And at the center of this diagram, you can see that message clearly. It does this by offering common unified audio and control interface that can scale up or down depending on the system complexity and power budget. So across all these platforms, from wearables to cars, the benefits of Swiss are consistent. Swiss gives you improved power and performance. It is built for power-constrained systems, reducing both active and idle power. It enables synchronized system operation, maximizes control bandwidth, and importantly, it delivers an error-tolerant control channel, which reduces glitches and retries in a noisy environment. So Swiss basically provides the necessary flexibility for system integrators. System designers get a choice of PHY, single-ended or differential, but the software remains unified. That means one driver model, one programming interface, and consistent behavior across products. And being a two-pin interconnect, it is great for compact and cost-sensitive platforms. So when we say Swiss is for all computing segments, we really mean it. It's a single, elegant bus that adapts to different physical environments, different power and bandwidth needs, and different levels of system complexity, whether you're building a battery-powered wearable, a high-performance laptop, or a multi-zone car audio system. Swiss brings the same foundation: synchronized, power-efficient, scalable communication for modern audio and control. And that's what makes Swiss a truly universal audio bus for the next generation of connected audio systems. So to summarize, last week we released Swiss specification version 1.0 for all MIPI members, which supports the features we looked at in this presentation. And now the MIPI Audio Working Group is developing Swiss version 1.1, where our focus is to add some of the new features like hub topology, where a peripheral can act as a hub, extending the Swiss link to downstream devices. And this allows designers to optimize each segment of the audio path based on, say, the physical layout or the EMI constraints and power budgets without changing the higher level transport or control protocols. We are also adding some features which will ease transition to Swiss, and we are making further optimizations to further bring, reduce the link bring up for faster peripheral attach and other enhancements. So please stay tuned to see what's coming up in Swiss version 1.1. Now, developing Swiss specification or Swiss interconnect has been a collaborative collaborative effort within MIPI's audio working group, leveraging contributions from leading SoC designers, audio device manufacturers, and IP vendors. And I do want to take a moment here to recognize the audio working group team here. It's their passion for audio, their determination, and their incredible technical talent, which has brought Swiss from concept to reality. So with that, I will hand over to Dervla.
Thank you so much, Aruni, and thanks to Neil and Christian. Really appreciate that presentation. But I will say most of the information that you see here, you can find at mipi.org. And again, encourage you to join MIPI and join the audio working group and get involved. So please do that. I see that there's a variety of questions that did come in. And the first one, slide 9. Can you please explain latency PDM bubble? Isn't SoundWire Swiss replacing older PDM interface?
We can go back to slide 9 maybe and see where that was. I think it's...
I think slide 9 shows PDM.
Yes.
Here, we really mean it as a data format. I think
Right.
if we take a peek at, for example, slide 27, we see, oh, what was it? This slide, I mean. If drawing your attentions to the dark purple and the orange and the yellow columns on the kind of the right side of that diagram, that could be 3 microphones, each with an opportunity to transmit every row. The rows are coming at 3.072 megahertz. So that's a typical PDM sample rate. And note that the quantizer in your microphone might be driven at the left edge of S1 every time, because that is a reliable audio quality clock you could be using for your quantizer. And then you put your data on the bus at the point allocated by your data port registers. And then that data is reliably conveyed to the other end of the link by the next row. So that's why we say that SoundWire Swiss has 1 PDM sample of latency for these PDM streams. So about 300 nanoseconds, which is just like PDM today. So I think that's the first question. So yes, we're replacing PDM transport with something much more flexible and higher bandwidth, but we're maintaining the same low latency of PDM.
Okay, thanks, Neil. Next question. Which companies make chips that implement Swiss?
I don't think we can reveal all the information about the companies that are working on Swiss, except for the ones that have come out and publicly announced that they have something for Swiss. But if you are interested in knowing folks who are interested in Swiss or will be bringing Swiss devices or implementations, please join the work group and you can see who all are there. But we cannot really reveal unless the companies themselves come out and announce. But I will mention that there is much more uptake and stronger ecosystem push for Swiss compared to previous interconnects. So we strongly believe that this is going to have a very good adoption rate.
Also, is it the case in the release the Swiss specification that just got released, it list the companies that worked on it, which
Yes.
Some of those companies may very well be working on chips as well.
Absolutely, yeah.
Okay. Next question. I've seen mentioned in old audio work group documents, both SoundWire XL and SoundWire Next. Did these become SoundWire I3S?
So yes, they wound up, all the best ideas from those wound up in Swiss, except for XL was designed really to extend the digital bus out of the phone around the user's head, specifically wired ANC headsets. During development, we realized that's not something anybody's really interested in. This was the fantasy that there would be an in-box headset with lots of microphones on each ear and performing ANC and the SoC down in the phone. And this didn't happen. So XL, a lot of the concepts in XL that were specifically to support that were abandoned. Although one of the things that did exist in XL was the concept of hubs, and those are coming back in Swiss 1.1 as a way to extend reach and manage traffic and emissions and power. So yes, Swiss should have the best of all of that.
Slide 16, do you have comparison with PDM?
We don't, because we are assuming you want a control channel for a bunch of reasons. So, I mean, you could make one, the link power PDM would be very, very similar to SoundWire Classic because they're both single-ended differential.
In slide 1516, do you have a chart for Swiss FB-CSE versus SoundWire?
No, and they're just very, very similar. If you Swiss FUBC and SoundWire are quite similar. I guess Swiss would be a little lower power for the same control traffic, just because of its more efficient control protocol. But otherwise than that, for the same bit rates, they're going to be the same.
How well adopted is I3S compared to the existing solution?
So, Rudy?
The specification just came out last week, version 1.0, but we can say that a lot of audio working group team members have been developing models and products while we were developing the specification. So at least from the participation in the working group, we do see a very good adoption rate of Swiss, but you will have to wait for these companies to come out in the open and announce.
How many wires are needed for single-ended PHY Swiss?
Swiss is just 2 wire. Whether you do single-ended or differential, it's just 2 wires. For a single-ended, 1 wire carries clock, the other carries data. And for differential, it's data plus and data minus. So it's just 2 wires.
Another question here to clarify, is each bit of a command, example, write a 32 command, sent in one Swiss row? So a complete command takes length of command Swiss rows to send?
Yes.
And maybe we can also say you can trade bandwidth of command to bandwidth of data. If you have just 4 columns, then of course you have a much higher command bit rate or bandwidth, and this you can use, for example, when you start the system. And then if you need, if you have set up the system and you need more data bandwidth, you just make more columns.
And what MIPI forum is available to ask for clarification on the spec visualizer, please?
Oh, you should join MIPI Audio Working Group or leave a note with MIPI team. And the visual, I think there was some question on where the visualizer tool is available. We have provided that link in this presentation, and it's open source, so you can get the tool.
GitHub. Yes,
Yes.
GitHub. Top
Okay.
3 reasons over A to B. Open standard, so you don't have to go buy your parts from analog devices. Lower latency, so if you're doing things like active noise cancellation in the car, you can get better performance. And more flexibility in trading off control bandwidth for data bandwidth, so you can have faster boot time for your car. What other? Actually, I don't think we've done an electrical comparison with A2B because it was proprietary, so we didn't.
I appreciate all of those questions that came in and that we were able to address them for you. So just to finalize, tomorrow will be the last session of this series, and that is going to be presented by Devin Worrell and John Eklund, and that's MIPI Audio Supporting Software Specifications and Tools. Thanks again, everyone, our presenters, and we appreciate your time.